Here's a few questions we had here. What did you mean by saying the spring force is very small? Did you mean the normal force is small? I'm not sure what I said. It was when we were talking about compressing, I think I meant the spring is stiff and the deflection is small. When you push on something or feel a normal force, it's like a really stiff spring and a really small deflection. It's probably what I was talking about at that time. When can we get the answer to the pledge problem? It's already posted, I'm pretty sure, on campus. So hit the pledge problem on the front page, the solution is there. Maybe I missed it. Why isn't there a negative sign in that last thing we did? Yeah, I was just doing the magnitudes. We're just thinking, how hard does this push? Sometimes we just do magnitudes. The negative signs just lead to more questions. And also, I wasn't doing a problem. Like compared with negative signs, we were doing a problem. We were just thinking about how hard is it to push on a normal force? You know, how springy is it? So I probably should have kept it in there. Okay, so that was springs, right? So now you know what Hooke's law is. We use it in some simple problems. You'll see harder ones in next week's homework. I'm going to put some of these problems in next week. But now we want to get on to like actual materials that deform. We talked a little bit about it. We said a normal force is an object deforming a teeny bit. But now let's put the numbers to it and get how we describe it mathematically. Okay, so let's see. So we're going to describe mathematically forces and deformations of objects. And I want to stress that there's really no new physics here, just new words. Okay? So this isn't like brand new laws that we have to learn or new mathematical methods. Just the names for things, I would say. But you got to learn a little vocabulary, even in physics, we have to learn a little bit. Okay, so we're going to do an object that looks like this. It's just a cylinder. Simplest object we could think of to start with. And this cylinder has a length L, that, and we're going to apply a force F to it, like that. Cylinder, we push down. And it's got an area, a cross-sectional area A. Look at that 3D rendering. We're going to apply a force F. But we don't really call it F, we call it the stress. All right, that's the force divided by the area. Say, isn't that a pressure? Yeah, it's a pressure. So we're not doing fluids right now, but that's basically a pressure, newtons per meter squared. So when you do that, we said you could think of it as a normal force, or you could say no, what's really happening is to cause deformation delta L. So what we're really going to do is we're going to make it shorter. We're going to bring it down to here. Probably not really that much if it's a metal, but we're going to make it shorter by delta L. And that is called a strain. Delta L over L. So this one is newton per meter squared. See, this one has no unit. This is like the fractional strain. We compressed it by 1%, but we don't put any units on it. Okay? So what we can do is see what happens if we push harder and harder. How much delta L do we get? That's all we really do. So we make a plot. So there's like engineering tools that do this. We're going to do material science. I think this is all you studied for 4 years. You plot stress on the y-axis, F over A, and you plot strain on the x-axis, delta L over L. And you see what the plot looks like. And it starts out, usually, depends on the material, as a line. This is what you went to college for. Okay, so it's a line for small delta L over L. Meaning if we're just a few percent, less than 1%, it'll probably be linear. Okay? We'll get into what happens when you go too far in a little bit. But at first it's going to be linear. And then the important thing that we define is the slope of that curve equals the stress over the strain. And that equals big Y, okay? Which is the Young's modulus. Young's modulus. So that is a an inherent property, or that is, what's the word? What's that word when it doesn't become the size? It's an intrinsic property of the material. So intrinsic of the material. So as you can imagine, you know, a sponge would have a low Young's modulus, steel would have a high Young's modulus. Soft materials is low, and it varies over orders of magnitude. Oh, I never could spell under stress. If it's a line, so what we can do now is turn this into Hooke's law. We can say, now wait a minute, this looks like force and X. It kind of looks like Hooke's law, doesn't it? So let's see. So let's go from Young's modulus to Hooke's law and see what happens. And we'll draw it. So let's see, we had F over A equals the slope, and then delta L over L. That's the equation of this line. The equation of the line, right? Y equals mx. If I write that, people will know here. I'll write it. This is unofficial when I write it here. That's just for your head. And there's no offset. There's no intercept. So we just said the y value is equal to slope times x value. So we can rearrange it and say, let's put this over here and get it in terms of f. And what is this? It's going to be y times a over L and times delta L. And basically, this is the spring constant. This looks like Hooke's law. F, so spring constant. K, we called before K, is the Young's modulus times the cross-sectional area times L. And that's extrinsic. That depends on the size of the thing. Right? So for example, a material like copper has an intrinsic Young's modulus, but if you have some geometry of a copper rod, and you want to make it into a spring, then you have to calculate its extrinsic property. You have to say it's this intrinsic thing, the Young's modulus, times the cross-sectional area divided by the length. And that's how it'll behave like a spring. Okay? Now you guys are really into negative signs. So where's the negative sign? So the people that were bothered by the lack of a negative sign before, let's think about where it is this time. If we were thinking of this as a spring, is this the right force? No. This is the force applied to the spring. Right? We want to know the force that applies to something else that's pulling on it. So we have to use Newton's third law. That's the deal. This is the wrong F. So F, as we've used it here, is applied to the cylinder. We need that F equals minus Fs, and this would be kind of like the spring version. Right, that would be if the cylinder is pulling on something, then there'd be a minus, and then you'd have a minus here. Then we're all happy. Then we have Fs equals minus, and then Y A over L delta L. And then we literally have Hooke's law. F that it applies to something equals minus a constant, how much it's different. What's in the bottom of the KEQ? I don't think I've written KEQ anywhere here. That's funny, I don't know. It's not fun, but everybody else is laughing. I don't know. Did I write KEQ somewhere? Did I walk into this? Are we laughing at the question? Oh, the K equation. Oh. I don't have a K anywhere.
Right here. It's that one. No, with the funny little K.
That is a spring constant. The spring constant is equal to, so what I'm saying is here, is this thing acts like a spring. Right? So we define these properties, this is like the engineering part. But if we write the equation of this line, we say, oh, it does act like a spring. The force is a constant times the displacement. F equals kx. So this is like the spring constant.
Is the loop-to-loop L the same as the big one?
Yes! That's it. There we go. We don't, I mean, this is like my passport, not case which, sorry about that. This lecture is rocking. It's like a rocket ride. This is like Elon Musk is taking us somewhere here. Man. All right.